What if I told you that the movie Butterfly Effect and the Doom 3 netcode have some parallels? In the past 2 months I've been talking a lot about FPS netcode and its problems. And naturally, a lot of people joined the discussion and came up with really good and feasible solutions like what if we just had quantum entanglement or time travel? Then someone argued that well, you could say that rollback is basically some sort of time travel. And as I was reading the comments, I was like, wait a minute. We kinda had that back in 2004 in Doom 3. So once again I started reading the Doom 3 source code, papers on the networking model, and then the rollback logic reminded me heavily of the movie Butterfly Effect, where Ashton Kutcher reads his diary, time travels, makes one small change in the past, and that changes the whole timeline. And I couldn't stop there, so I started digging, and turns out that the Butterfly Effect came out like 8 months before Doom 3. So today I wanna do 3 things. First, I want to show you how we even got here, because Doom 3 didn't just spawn this idea out of thin air. This was an evolution over multiple generations of the id Tech engine. Then I'll show you what Doom 3 actually did. We're gonna take a look at it from a top level, how the netcode was designed and why it reminds me of the butterfly effect. Then we're gonna see how it's actually implemented in the code. And finally, I'll talk about the ugly reality. Why this sounds incredible on paper, but why you don't just ship Battlefield 6 with Doom 3 netcode and call it a day. As always, you can find links to all my sources in the description, and if I got anything wrong, feel free to correct me. Okay, now how did id Software come up with this? To understand that, let's do a quick id Tech engine evolution speedrun. And stay with me, this is very important to generally understand some netcode things. Okay, as you can imagine, multiplayer shooters like classic Doom didn't start with Subtick. They started with something much more optimistic, let's put it this way. The classic approach was lockstep. In old school Doom, everyone runs the exact same simulation. And instead of sending states, you send your input commands for each tick. And when I say everyone runs the same simulation, I mean before advancing the game, everyone has to get everyone else's input. So everyone sends their input for, let's say, tick 1, 2, 3, and you will not advance until you get the input from all the other players for that tick. You wait, which is fine on LAN and absolutely cursed online. Why? Because the moment you add real latency, your entire game becomes turn-based. It's more or less unplayable because the player with the worst latency basically ruins the game for everyone. This is also very common in life where one person ruins it for everyone. Like, for example, when you're on a party and someone starts playing a guitar. Nobody wants this, okay? Put it away, John Lennon. You're making it awkward for everyone, okay? So that's when people decided, let's start cheating. Cheating reality. One of the early big steps in FPS networking was client-side prediction. A lot of people casually credit Quake World for this, but historically, the Duke Nukem 3D build engine was the first one, and the game also had strippers. So the idea is simple. Your client moves you instantly and the server can correct you later. And that's basically the foundation for the modern setup. Server is authoritative, but your own movement gets predicted so the game doesn't feel like a slideshow. And then we fast forward to Quake 3, where we actually have all kinds of optimizations and a very mature netcode architecture. But keep in mind, Quake 3 didn't have server-side-like compensation like Counter-Strike. So it was server authoritative, it predicted only your own movement, interpolated everyone else, meaning you were basically rendering other players in the past. So logically, you had to lead your shots. Okay, finally we enter the era of Doom 3. In Doom 3, Carmack went full deterministic and said, what if we stop rendering the past? What if we predict everything we can currently see so the world you aim at is closer to now and not a delayed recording? They introduced some Michael J. Burry level prediction. And that's where the butterfly effect rollback loop comes in. Because the moment you predict more than just yourself, you are going to be wrong sometimes. And when you're wrong, you need a correction strategy that doesn't turn the game into a Cyberpunk launch release. So before I dismantle what Doom 3 actually did, I want to show you this. Turns out only 5.1% of my viewers are subscribed to the channel. So if you like the content, a subscribe would really make me feel better about my life. Alright, before we touch a single line of code, I'm gonna give you the right mental model for what the client and server are doing. And I'm gonna use the movie Butterfly Effect as an example. In the movie, Ashton Kutcher has this diary. He reads a page and gets dragged back into that moment in the past. He changes one tiny thing, comes back, and the whole timeline is different. The present he was living in was just one version of reality, built on a page from the past. And that is basically Doom 3 Netcode Rollback. You still have the normal client and server split, where the server is authoritative, but unlike Quake 3, your client doesn't just sit there interpolating old snapshots. It predicts forward and renders that predicted now for a few frames. And not only for you, but for everything in your potentially visible set. The whole point is, the world you aim at feels more current, so you don't have to lead your shots. That means you have two timelines running at once. The server is the real timeline, and the client is a predicted timeline slightly ahead. Okay, now the server sends snapshots, aka diary pages. But listen, every snapshot that arrives is from the past, from your perspective, because you are actively predicting the world. So when the client receives it, it applies it to that old moment and overrides its state with the server truth. And this is the rollback part. Once it overrode the past state, it can't just continue from where it was. The history, just like in the movie, has changed. So it jumps back to that corrected moment and then it re-simulates forward until it reaches now again. That's the rollback loop. Jump back, apply the change, fast forward, and now your present is consistent again over the whole timeline. If the snapshot matches what the client predicted, nothing happens because the history didn't change. But if it doesn't match, you have to re-simulate, re-predict the states. And you, as a player, you don't see this rewind on the screen. The game isn't re-rendering the past on your monitor. Those frames are already gone. They're gone like the dinosaur in Tekken 3. This rewind is internal. It's just fixing the old state so the client can predict forward from the correct starting point. So if you compress this into one clean loop, it's basically this. Client predicts little into the future, server sends a snapshot holding the true game state but from the past, snapshot arrives and corrects the past moment, client uses the snapshot to confirm his state or to re-predict the future states. And that's the butterfly effect nature of Doom 3 netcode. One tiny correction in the past can rewrite the present and the future. So the client keeps itself sane by jumping back and replaying forward. Now, coming up with ideas like this isn't magic. It's having a feel for logic, cause and effect, constraints, and what has to stay true for the system to remain consistent. The good news is, that kind of logical intuition is absolutely something you can develop. And if training that kind of intuition sounds useful, you will love today's sponsor, Brilliant. Brilliant helps you learn through active problem solving. Not just watching videos and hoping it sticks. You're constantly answering questions, trying approaches, getting instant feedback, and stacking small wins until the concepts click. It's the difference between, yeah, I heard about algebra, and, oh, I can actually be cool at parties now. The courses are built by an award-winning team from places like MIT, Harvard, Stanford, Google, and other organizations that rejected me in the past. Most importantly, it makes you a better thinker. You're not memorizing formulas, you're working with ideas until you get that aha moment and can solve problems on your own. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Tariq10x, scan the QR code on screen or click the link in the description. Brilliant's also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Okay, now let's get into the code. By the way, I'm planning to make a very detailed Doom 3 code review. The last one I made was my first code review on this channel, and I know I can do it much better now. Okay, when it comes to the actual implementation of the snapshots and rollback, we're gonna take a look at three key pieces. First, how the server builds the snapshot. Second, how the client reads the snapshot and builds the entity list. And last, how the client predicts that list. So let's start with how the server builds the snapshot. Okay, so Doom 3 has been open sourced. A link to the GitHub page is in the description. So what we are looking for is in the game network file, in the function server write snapshot. Now, a small disclaimer for my software engineering colleagues. This video is not one of my code review videos where we go really deep into the C and C++ coding details. So I'm gonna keep everything few abstraction levels higher than usually. But I will do a new full Doom 3 code review video where I will go into the finest details as you are used to from my videos. Okay, so this function creates snapshots of the current game state for a given client. It starts with a bunch of definitions and then it starts building the snapshot. So first they free the old snapshot and then they allocate memory for the snapshot. Just like in their previous engines, they've written own functions for memory allocation. I've talked about the reasons for doing this in my previous videos. And then we start looking at the current PVS, potentially visible set. So this PVS handle does exactly that. It asks, what can this player potentially see from his current position? And then when we have the PVS, we start building the snapshot. So the function now loops through all entities that have been spawned in the game and checks, is this entity in the player's PVS? If it's not in the PVS, we skip it with this continue. If yes, we mark it in the snapshot PVS bit field. This is bit packing optimization. Every entity gets only one bit. I know Counter-Strike 2 Reddit fanatics probably never heard about this. They are too busy defending Valve. And Valve can't fix the netcode because they are too busy thinking about new slot machine mechanics for the skin market. Loot boxes and gambling. Anyways, then we have the network sync. This is basically saying, do we need to network sync it or not? If we need to sync it, then we need to write it to the snapshot and delta compress it. And then we write the entity bits to the snapshot. So after that, the function creates a new snapshot base. Since in Doom 3 we have a common base to delta against it, it's not using the Quake 3 approach where we delta against the last acknowledged snapshot. And then at some point when we are done with all the entities comes this. Message, write bits, entity num none. In case you're wondering, this is a terminator sequence. When you read it on the other side, you know this is the end of the message. As I said, I'm keeping the explanation on a very basic level, so I don't want to go into the fine details here. Okay, now let's take a look how on the client side the snapshots are being read. Now, as I said in Doom 3, the server and client functions are basically in the same file. There's no split like in Quake. Okay, so if the Lago meter is on, we need to update it. If it's off, we can skip it. And now again, just like on the server path, we start clearing the previous snapshot entity list. We allocate the memory, and then we start reading all the entities from the snapshot. And here is the terminator I have mentioned. So this function's whole job is to take the server's snapshot and bring the client up to date so it can predict and render the next frame. We clear the old snapshot, allocate a fresh one, and jump into the first loop. The first loop reads every entity the server sent. Then once the server thinks you might see, respawns any that don't match locally and overrides them with snapshot data. It stops when it hits this terminator marker. Okay, now let's take a look how that list actually gets predicted. This is where the prediction happens. So we loop through every entity in snapshot entities, which is every entity in your PVS. We enable the physics thinking for this entity. The thphysics flag tells you need to run physics on this tick. Okay, this is where each entity simulates itself forward by one tick. It basically runs the same physics code that the server runs. And so in one loop, Doom 3 predicts every visible entity forward. And that's the fundamental difference from Quake 3. In Quake 3, you predict your player, if you remember from my Quake video, and everyone else is interpolated between two past snapshots. Okay, now another important fact is the rollback is not an infinite rollback. It is limited by these CVAR variables or console variables. So this means the client can run up to 1000 milliseconds ahead of the server. That's roughly 60 frames at 16 milliseconds per frame. But in practice, the client usually runs 5 to 10 frames ahead, depending on your latency, of course. Now you might be wondering, or maybe not, but how do you predict other players? You don't have their inputs. Well, actually you do. The server sends the most recent inputs from other players along with the snapshot. If you look at the snapshot structure, the server doesn't just send entity states, it also sends the last known user command for each player in your PVS. So when your client predicts another player, it's not just extrapolating randomly something, it's running actual player physics with your actual inputs. The Van Waveren paper describes it explicitly. The server sends the most recent input from other players with snapshots. This input from other players is used by a client to accurately predict other players. And here's the trick. So the client is doing real prediction, not just dead reckoning. And because it's using real physics with real inputs, the prediction is surprisingly accurate. The paper even points out that the Quake 3 bots proved this was feasible. They used algorithmic prediction of player movement and were very accurate. Doom 3 just does this for other players. Now, Doom 3 also has explicit smoothing controls for error correction. If you do hard corrections, things will jitter like crazy. These controls are console variables. They control how aggressively the client smooths corrections. The values range from 0 to 0.95, which means from like no smoothing at all, which causes hard snaps, to very smooth, slow convergence. But now a very important part of this whole smoothing concept. The physics state gets corrected instantly, so the simulation stays right. But what you see on screen eases toward the corrected position over a few frames. And that means for a short moment, the physical hitbox doesn't perfectly align with what you see. This is also why even in modern FPS games you sometimes shoot right at a guy and it feels like hit reg is broken. There is a good chance you're aiming at a smoothed visual, but the server is judging the real hitbox. I think we already mentioned this, but Doom 3 doesn't do server-side lag compensation like Counter-Strike for example. The server still evaluates shots on the server state, but because your client is showing you a predicted enemy position, it can feel like you can just aim at what you see and shoot, without leading your shots. And that was basically the whole idea. I'm not saying it worked flawlessly on high ping, but compared to other games with server-side lag compensation, Doom 3 punishes high ping pretty hard. If you have bad ping, you're gonna shoot and miss a lot more, while the low ping player just has a smoother, cleaner experience. And if you ask me, that's honestly more fair than trying to equalize bad internet and then ending up with people abusing lag switches, farming peaker's advantage, and turning your gunfights into a networking exploit contest. But if this Doom rollback approach has all these advantages, why we don't just do it in modern FPS games? And this is the part that always kills the dream. It only works under certain conditions. So let's talk about the downsides. Alright, on paper this sounds like the solution to everything. Predict everything, rollback when wrong, less I died behind the wall. But the moment you scale it up, the math starts beating you up like prime crow cop. First problem, cost. Rollback isn't simulate n entities, it's simulate n entities over x frames. Doom 3 could get away with it because it had these tight indoor maps and a very small player count. You're not tracking 40 dudes riding helicopters across an open map. Modern shooters have bigger maps, more players, more everything. And now your rollback frames turn into CPU spikes and frame pacing hell. Second problem, determinism. This approach wants the client simulation to match the server simulation perfectly. Any floating point weirdness, timing differences increase mispredictions, which means more corrections, which means more visible artifacts. Third problem, latency still exists. You're not deleting delay from the universe, you're just moving the pane. Instead of server rewind problems, you get correction, smoothing, weirdness when the server later disagrees with what you saw. And the last point is level design. Doom 3 has these corridor-heavy maps for a reason. Occlusion keeps your relevant set small, which keeps prediction cheap, which is the only reason this is even feasible. On big open maps, it would explode. So yeah, it sounds like a silver bullet, but it's a silver bullet that only fits a specific gun. And most modern shooters are not that gun. Conclusion. Could this solve a lot of issues if we had unlimited processing power, unlimited bandwidth, and low latency? Sure, but also if we had unlimited processing power and bandwidth, all the other approaches would work too. You could crank up the tick rates, crank snapshot rates, shrink buffers, and basically brute force your way through half the pain. So the interesting part about Doom 3 isn't, wow, this is the final answer. The interesting part is that it shows a different solution space. It's a fantastic fit for a very specific type of game, like fighting games. You have a small number of players, a very narrow space your character can move in, and if you design the moves with rollback in mind, you can build the animations around it so the gameplay still looks smooth even when corrections happen. And I think that's the real reason why it didn't translate into modern shooters. You gotta keep in mind that netcode is still one of the hardest parts of online multiplayer, because you're trying to make one game feel good under a giant set of random variables that keep changing during the match. You have different latencies, different frame rates, different network stability, different match sizes, map shapes, and different expectations. And you can't optimize for everything all the time. So when people say just add rollback, they are not wrong per se, but rollback comes with its own set of trade-offs and its own fallacies. And that's the real takeaway. The best netcode is not a single technique. It's the technique that matches your constraints, your game design, and what kind of pain your players are willing to tolerate. Now, I want to take the moment and say a big thank you to everyone who supported me over the past year. As you know, I'm juggling these videos with a full-time job on top, and honestly, reading your comments is what keeps me motivated. If you want to support the channel, there's a Patreon link in the description. You can become a YouTube member or just leave a comment. Comments really seem to help the algorithm pick up my videos. So that's it for today. If you like the content, then like and subscribe, and see you in the next one. Tariq 10x.